Okay, so I won't waste many words of thanks for making all the effort of bringing me here. I'll try to make up for that with some interesting lectures. So what I'm going to talk about is how to extend the EFT as introduced by Daniel and David in the first week to larger objects. So meaning larger in terms of numbers of particles involved. What Daniel ended up with was the discussion of the three-body system. So what I want to, this is where I want to connect and then tell you not something about solutions, but mainly about problems we are facing at the moment in how to extend this EFT program, the pionless contact formulation of it, to larger objects. But first of all, before going into that, I want to tell you why we are doing that. And I think this is most important. I mean, we're not doing it for the sake of it, but the EFT should give us some idea or some solutions to problems where other approaches fail. For that, I want to discuss this plot, which is a generalization of the famous Yefimov plot. And if you're not familiar with that, what you're looking at is a spectrum, not only of the three-body system, but also of the up to the six-body system. On the x-axis, you are plotted the inverse of the two-body scattering length, and that is a substitute for an interaction strength. So the interaction strength increases from left to right, and all the lines you are seeing resemble states in the respective systems. So to the very right, you see that at 0, corresponding to an infinite two-body scattering length, the various thresholds there open up, which correspond to bound dimers. So an infinite scattering length corresponds to a bound state at 0 energy, right at threshold. The black lines are those thresholds, and the other lines, red, purple, blue, and green, you'll see that they develop bound states way earlier. So the interaction strength, let's say to the very left of that plot, is resembling an attractive interaction, but the attraction is not strong enough to bind anything smaller than the hexamer. So at that point, you have a very weakly attractive interaction, which only binds 6 bosons, but it leaves the 2 up to the pentamer system unbound. Okay, so what's the whole problem with that point? So what I want to give you a different perspective on is this phenomenon which occurs for the three-body system, namely this accumulation of an infinite tower of bound states in the three-body system, called the Yefimov effect, but I don't want to invoke that term too often. It's simply in that in this lecture a sequence of an infinite tower of bound states, which happens at this point, namely where the interaction strength is tuned to a point where the two-body correlation length becomes infinite. And at that point, this peculiar phenomenon happens that although you have no scale anymore at the two-body level, you develop the scale at a larger system in the three-body system. Okay, this is well understood. I don't know how much Daniel told you about that. I will rederive that from a slightly different technical perspective, which allows us then also to understand what happens in the four-body system. So this is the natural question to ask. So if I have this phenomenon occurring at this critical coupling strength where the two-body interaction develops a bound state at threshold, does the same thing happen for three bodies? So this is what I try to sketch here with this cartoon. So the thought experiment you should do is take your favorite two-body potential, parameterize that with the coupling strength, and then begin to increase this coupling strength up from 0 and make it more attractive. If you do that, at some point you hit this 0 bound state for the two-body sector, but before that, you have a critical coupling strength where the three-body system develops a bound state also at threshold. And then the question is, what is the four-body spectrum doing at that point? So does it also develop this infinite sequence of bound states or not? Does it introduce a new scale? And this is the fascinating question and quest for all that business. Can we find another one of those phenomenal things and new scales which are not peculiar to the three, but to larger systems? Because this is the basic understanding of this Yefimov effect, that you have a scale which develops decorrelated from the two-body system, where there is no scale anymore. So what I want to do on Thursday is to use the same technology which we are applying today for the three-body system to demonstrate that something like that doesn't happen for the four-body system. So this will not repeat itself. This is still something you can prove more or less analytically, and this is why this is the only slide I'm going to use. Yes, and this is one of, so those are solved problems. Now, why we are after an EFT which goes beyond that. So I wrote down a couple of things. So what we also see in that plot, and the thing of that plot is that it's been calculated numerically. So there is a certain feature appearing here where you see that to each of those pentamer lines, for example, so the blue line here, you have a seemingly correlated pair of a very shallow with respect to that threshold state in the six-body system and a deeper one. And this pairing of cluster states attached to those universal smaller systems, this is something which has been empirically found by numerical calculations, but we don't understand it. So this is one of the deep questions to understand. First, are there only two of those states? Are there more? Computationally or numerically, we only find those two, but we always find this pattern of two attached to the so two hexamers attached to a pentamer state, two pentamers attached to a tetramer state, and so on and so on. And so this is why I picked this problem as a motivation for developing an EFT for those larger systems, because this is something we want to understand and we haven't. So if you have a good idea, if you see any flaws in the derivations, if you know what to look for, this is one of the bigger problems. The other one is something about finding out where those critical system sizes are for a given interaction. So there are instances where the two-body system is unbound, so helium-3 atoms, for example, and where the question is also experimentally, what is the smallest number of those objects I have to bring together such that they sustain a self-bound system? And the number which is conjectured or argued using models is around 40. But to have a more solid, rigorous derivation understanding of that critical system size of a self-bound cluster or droplet, this is also a challenge for EFT where we can get rid of all model dependence. Okay, with that motivation aside, let us start with the discussion of how we understand the development of this tower of three-body bound states, following up on where Daniel ended up with. So in general, universality, if I invoke that term, yeah, and I thought it goes without saying, so you just interrupt me if I'm using jargon or so. I know that one of the main motivations here is to bring together particle physics and nuclear low energy physics. So I will use words which are not or have even a different meaning in your community. So universal means most generally independent of short distance structure of the interaction. So a universal, so all those curves here are supposedly something which do not depend upon how this two-body A emerges from a two-body interaction. So I can replace that interaction and most of these curves will only move very slightly. And as soon as this happens, so that those states do not depend upon my specific model or interaction, which produces or is calibrated to that two-body scattering system, then I refer to that as universal. These calculations haven't been done for a variety of potentials. So I'm not sure to what extent those curves I showed were actually universal in that sense. I expect that, I conjecture that especially those deeper curves will be very sensitive to the two-body interaction model used. Nevertheless, this correlation between, so the curves themselves might shift, but they will shift together. This is the one of the other things which we don't understand. Okay, so how do we find that spectrum here? And the equation used, and also here I don't want to use too many words where the they have equations which gave you a decomposition of the ordinary Schrödinger equation or Lippmann-Schwinger equation into a matrix equation. Let's give that an index 1, 2. Okay, this is an equation you should recall from last, or not you should, I don't really know, but I saw that equation on Daniel's slides briefly. What I want to give you is a short intuitive explanation of what and why that kind of decomposition of the total wave function into components has been done and what has been achieved there. So the various components have been defined as G0, V I psi. And this is based on a certain classification of diagrams of this operator here. So where it comes from is just the ordinary Schrödinger equation plus V acting on the entire wave function E psi, where this V is given as a sum of, in this case, two-body potentials. So I don't want to introduce three-body forces or anything more complicated. This equation should hold also for any kind of system. Now specifically for the three-body system, what I want to discuss on Thursday was the more general approach to n-body, a-body systems. But for now, to get the idea behind this decomposition into various components, it's, for me at least, easiest to do that on a diagrammatical basis. So if I do that, and then what we do is we rewrite that equation slightly, such that now what do I? Yeah. So you'll bring that to the other side, V to that side. Sorry, I need to cheat. Not that. Yeah, so first, let's do reverse engineering. So that means in this definition of psi I can substitute back in this sum which defines psi. So this is nothing spectacular. So I get psi I is equal to G naught V I, and then a sum over all other psi j's. I can single out one of them, which is identical to the component I'm looking at. And what I get is then 1 minus G naught V I acting on psi I. And that is equal to G naught V I. And then the sum over those components, which I'm not looking at. This operator here, I can invert. Y is something we must be careful about. But the very beginning, so yeah, I'll come to that later. Okay, so I invert that operator, and what I'm left with is then a, sorry, this gets a bit confusing, psi I, which is equal to 1 minus G naught Vi to the minus 1 G naught Vi, and then the sum over J naught equal to I psi I. And the usual trick now is, so in all this business, you will, or I always get very confused with T matrices, Green's functions, wave functions, and a couple of other operators which are defined in order to make the problem you're looking at most transparent or mathematically tractable. But the one thing which reoccurs always is the usage of geometric sums. So, and geometric sums in that here, if I expand that as a geometric sum, what I have is 1 plus G naught VI plus G naught VI, G naught VI. Sorry? Psi S.
Finally, sum over S not equal to I. Above. Yeah. Right. After that.
After that?
Yeah. Then psi. Superscript N.
S J. Sorry, that was a J. Yeah. Yeah.
White.
Right. I should have used white. I don't know why I used blue. Sorry. Yes. Okay, that then G naught VI. Yeah, and then the sum over J not equal to I or S of that. Okay, so now I multiply that in, I factor out a G naught to the left, and then comes the what is defined as the T matrix, VI plus VI, G naught, VI, sum over J. I. And this sequence here is what we define as TI. Okay, so this, and this is G naught. So this gives us the equation G naught, TI, and then the sum over J. And what I've done here is now just, I've re-derived this part of the equation. So if you look at that, psi I is equal to that sum. Those T matrices here are the T matrices defined for the interaction between particles which are not equal to I. And this is just the matrix formulation of that. This inhomogeneous term is the one which I have not accounted for here, because what I have assumed is that I can invert that operator, and that assumes that, and I can only do that if this term vanishes. So these terms here, they correspond to asymptotic solutions where a bound state of two particles evolves freely at infinite time or outside of the interaction region from the spectator particle I. And this is something where I need to be careful about when inverting these operators. And that's why what I've done over there does not recover that term here. When this is always possible is if the energy is smaller than 0. So in that case, there's no problem with the inversion of that operator. And therefore this equation here for the homogeneous equation applies to bound states, and that is what we want to analyze. So the three-body equation of interest now becomes that one. Which is still a coupled integral equation. A coupled integral equation. for the three components of the wave function. And this, encodes or should apply for bound states only. So where does the energy come in? This is in this G0. To make this more explicit, this G0 is the inverse of some energy minus H0. And that makes it, obvious that if E is smaller than 0, there's no pole in that, so I can take the inverse at least formally. All right, so I'm not going to talk about scattering solutions, but to remember that, so this version or any Lippmann-Schwinger equation encodes the boundary conditions explicitly via this inhomogeneous term or the absence of it. And this is a difference to the Schrödinger equation. If I just look at the Schrödinger equation, solutions to that might be scattering or bound state solutions, which I cannot tell by just writing down the Schrödinger equation. From the Lippmann-Schwinger equation, I can immediately tell what kind of state I'm looking at. Okay, so this is a lot of technology. And this is actually what has been used for a long time now to find bound states for a given potential. So where does the potential feed in? And it feeds into the T matrix. So for any given interaction model potential theory, you have a defined T matrix here for the two-body subsystem. And you can make any effort or go through any loops to solve that equation. This is not what we want to do. So this is all nice, a lot of numerical work. What we want to analyze is more analytically what we can extract by just considering certain features of this so-called kernel operator. So is there any kind of feature or property which we can analyze without relying on numerical models, which can tell us something about a phenomenon happening in certain limits? Why is that so interesting? Because this decomposition here, what we've done for the three-body system, is something we can generalize. And if we are able to say something about a specific limit, and if we are interested in those, in this Yefimov scenario, the limit which we should look at or be interested in is that one where this energy goes to 0, corresponding to a certain interaction strength. And at the same time, where so this energy is the total energy of the system. So this is important to realize. And then independently of that, I want the two-body subsystem to develop a bound state at threshold, and that corresponds to the scattering length going to infinity. And both of those then make the connection to what has been discussed in terms of EFTs in the first week. So this is where everything matches together at this two-body amplitude. So this we can calculate for any potential, but what we know now how to calculate it without qualification, but what we know now is how to extract that from field theory, from an effective field theory. And this is what we want to do now. So to consider the limit, what happens to that operator here if the total energy goes to 0. So if I'm looking at solutions to that equation very close to the threshold, and at the same time for an interaction where the two-body correlation length diverges.
These should be small.
Not necessarily. Yeah. So so formally I can write this down. Whether or not it converges is another question. But this is just an operator identity at the moment. It's not yet numbers. Those are just operators.
Very similar thing.
Yeah. So once I want to approximate that, I mean, it's nothing but a power expansion. But if I'm always writing this as an infinite series, this identity holds. So regardless of if it's small or large. But yeah, so this object here might be infinite. That's something I don't know. So there was one thing, so I haven't written down any diagrams yet, but maybe, not that we have to, but it's, so let's start with that. So what is this operator here, this TI? So TI is defined for a very specific interaction here, and here we can make the connection or look at a diagrammatic representation of that. Again, this is something I want to do more rigorously one of the next lectures, but this would be just a repropagation of the particles. Here I have the interaction between two and the free propagation of the ith particle. This one here would be an iterated interaction, and so on. So the usual notation is slightly different here from what has been used so far. So this is not an exchange of a photon. It should just tie together those two objects. So if what has, I think, been used last week was that one. So what you have is this bubble sum, and this has been evaluated last week, right?
If I take minus H naught to be delta, then the G naught ordered of delta. So basically multiple insertions of delta.
Mm-hmm.
That's basically what you do.
Yeah.
But in any case, it's still required to be small, but I put B equals to, but D0 B equals to, let's say, 2. On the left hand side, you get 1 minus 2 minus.
So for this series to converge, so so I'm more used to going the other way around. So I start with this perturbative expansion based on an interaction in a field theory. So each of these vertices is my my 4-body pi to the 4 interaction. And then I consider this perturbation series, and I'm asking whether or not it converges. So and then I realized that if I want a bound state to emerge, that each of those diagrams here is the same order. So they are all equally important. So I can't truncate that series at any point. So I sum it up and I forget, and then I rewrite it, or I interpret it as a geometric sum and write it like that. And now I need to be, so what I'm doing there, it's each of these terms is, so it's a complex function of the energy. Okay, so I'm not too familiar with what allows me to formally identify that infinite series with that piece here, if the series diverges. No, with that I disagree. I can't say that the potential is small, even if the potential might be extremely strong but short range. So, or I don't know what strong or weak means in that context. I don't have a comparison, but so I think it's an argument about analytic sums where and then understand that as an analytic continuation. But I don't want to be too okay. What I wanted okay, but what we have here is now that we recover this this bubble sum in the formulation of that three-body operator here with a spectator particle I. So the formula, and that is where I want to be now specific in terms of representation. So this is just operators acting on a wave function without specifying the representation. And now to get something quantitative or qualitative out of that, we specify the representation to momenta. And for three particles, a very convenient choice of coordinates is the simplest, is not single particle coordinates, but so-called Jacobi or relative coordinates, where I have a relative coordinate P between two particles and a relative momentum Q between the center of mass of the interacting pair and the spectator particle. And in that representation, I want to analyze this Ti, and then becomes a bit more easy to look at. So P, Q, Ti, prime, Q prime. So this operator here, or here, so it only acts on the P state. So it doesn't affect Q. This is why this choice is so advantageous, and it has to be made depending on what I am looking at here. So here I then get a delta function, Q prime minus Q. And the T matrix, P, T, I. And this object here is what we have evaluated last week and what we have an expression for. So I don't think, so what David showed you, hopefully, was how to get that in PDS renormalization. Yes, no? So let me just, what I want to do is something slightly different. But yeah, so in PDS, this should give you a relation between the inverse of the coupling or the low energy constants So I don't recall the numerical value here, plus and then another number I k. Yes, so if I made a, so I lumped all the numbers I don't recall and the 4 pi's and so on into those constants here. But depending on to which order of your theory you are considering that two-body amplitude here, you get more or less complicated inverse sums of low energy constants here. And this is something which is then in the renormalization procedure matched to some experimental amplitude. And at leading order, this recovers the 1 over A. So I choose my low energy constants here along with the renormalization scale such that this term here becomes an experimental datum. And in that case, it should be the inverse of if I parameterize the amplitude with a scattering phase, k cotangent delta minus plus ik, and this in an effective range expansion, which introduces the scattering length now is to be matched, or the low energy constants have to be chosen such that they reproduce this 1 over A. But this is then encoded in those low energy constants, and this becomes important later on if we want to discuss the convergence of that object here. Another possibility is not to use PDS, especially for or to make a connection to what has been done in traditional nuclear physics, but also in terms of numerical implementations, a cutoff function regularization is more advantageous. And in that case, you introduce a cutoff parameter and a cutoff function, which attenuates the large components of your momenta in this amplitude. And the, no, this is, you can't read that anymore. Right? And that becomes, why do I use K and not P? And why does nobody ask me that? Where the hell K comes from? So at leading order, this will become lambda squared u dq e minus q squared. So this is, I don't think you can read that, but this is just the cutoff function regulated version of that amplitude, where at each of those vertices here, instead of regulating the loop via Dirac, and you introduce cutoff functions, and and that also makes the loop integral finite. Those cutoff functions appear here then in the amplitude and also in the denominator. And what I forgot was the plus I p. Okay, so now that I have that, so for lambda, the cutoff should be something which is beyond a certain scale, but except for that, it should go up to infinity. So I could take any lambda I want as long as it's not too small.
You are doing an expansion first. With an expansion is 1 over mass, right? So when you start with the Schrodinger stage for the stuff, right? That's already expansion below the mass.
You mean in terms of relativistic kinematics? Or,
yeah.
Yeah.
So that's the exact validity of your theory.
That's the max.
That's max. Max cutoff. But then there is a 1 over a that gives you a different scale. Right?
Mm-hmm.
So you can't take it to infinity, right? For example, Dimre is a different scale.
So I don't understand this. So with this cutoff, I control what kind of loop momenta I allow to propagate in here. And yeah.
Then I can do a particle antiparticle. That is not allowed.
But it is not part of my theory. So there is no way I can see that. Yeah,
in practice, what do you do?
So in practice, you're limited with that lambda by numerics. So that is all. So there are some attempts now to do that more rigorously, analytically. So one of the experts is in the room, but yeah, fundamentally there is nothing which keeps me, or even which would justify to stop my analyses at a certain lambda. Whatever I calculate must be independent of that scale. And removing it would mean taking it to infinity. So and the fact that those momenta I'm then having in my loop are something which are absolutely not within the area of applicability of my theory is, yeah, doesn't hurt or doesn't show up in an observable quantity as long as I'm making my low energy constants lambda dependent, which compensate for all of that stuff. So this is how I understand it. So, but to answer your question finally, so what we are typically using is something which is so if A in nuclear physics, this A is of the order of, yeah, let's say 20 Fermi. And typically cutoffs we are using are usually in momenta, they go up to, yeah, 10 inverse Fermi. So that is about where we are limited. Okay, so how much? Oh, okay. So the next thing we need to discuss is now, what can we learn from, so is there anything we can do feeding that structure here into this equation? And we can simplify this equation further by knowing that what we want to discuss are identical bosons. So for identical bosons, this equation simplifies, and we can do that separately, but what happens is that instead of 3 independent components for identical particles, what I get is just a single component out of that, because I can construct certain permutation operators which turn this into the other J's, and I write those down in a minute. So G0, T. Then comes this permutation operator, which is 2, 3, P 1, 2 plus P and then the same component. And from so this is not something, this is straightforward, which doesn't mean that it's simple. And I hope you'll let me get away of not demonstrating that explicitly, but I just wanted to get the permutation operators right. Not that this is also wrong. 1, 2, 2, 3. Yeah, so that reduces the set of equations to a single equation to be solved. So the permutation operators here, yeah, do what the indices indicate. So exchange particle 1, 2, 2, 3. And after you solve that equation, you build the total wave function as, yeah, as the operator 1 plus this combined permutation operator here acting on this component you get out of that. This T is now something which you can choose for whatever pair you like, and then solve this equation. So this, again, it's a straightforward, nevertheless very complicated exercise to write this down now in momentum representation, and for the sake of time, I skip that and just write out what we get from that. And so this becomes the Green's function E over M minus 2 squared over M, then an integral over P prime, then the same structure, just with Q interchanged with P prime. And psi of U yes. Okay, so since I'm already over time, so this is where we'll continue next time very quickly. So now we have an expression for the integral operator, which we can analyze. So we still need to find a solution to that. But what will happen is, or you can already write this out if you are ambitious, to solve this equation, then make an ansatz for psi, which introduces these, what is in the denominator? Square. So for the, again, this is a bound state equation. This is an ansatz we can make for such a bound state. And that yields an integral equation now for this psi. And in this integral equation, we will find a kernel operator, which has, which is very benign in terms of being able, revealing these properties in the limit of E going to 0 and A, which gets in through that matrix here, or our EFT amplitudes, going to infinity. And in that operator, we will see that it diverges, or not the operator itself, but its trace. And the trace is related to the sum or the number of bound states. And this makes the connection. And just as a teaser to, if you get lost in all this slightly technical stuff with a lot of mistakes, the same procedure we can then adopt to larger systems if we are able to generalize this equation, or if we understand more generally what this operator here is. So if we, and this will be the connected part of the subsystems. So what you can see here is you have a G0 operator, and then this amplitude, which connects the subsystem in which the scattering length or the binding energy approaches threshold. And this is something we can generalize, so that we always analyze that piece of the kernel operator in the bound state equation for an A-body system in terms of the analytic properties of the connected piece of the system, which is reduced by one particle. But this is then something for the next hour. So if there are, or if you're not asleep yet, you mean the G0 as a 3x3 matrix? G0 is not a 3x3 matrix. No, even that is not a 3x3 matrix. No. So psi is a sum of, I decompose psi in a sum of 3 components. And what that was a bit confusing. So what I did here now was, so those components were defined as such. And then I want to find equations of motion for these components. And that then introduces this matrix notation. At this point here, there's no matrix formulation. I don't see that. So where it's clear is here at this point. So here I have psi I is equal to that times a sum of things. And that is what I translate into that. You don't know that. You get it from this short calculation. So here you see. So let's write this out for psi 1. So if this is for psi I, for psi 1. What is this? This is G naught times T1 and then times psi 2 plus psi 3. So this is always the same, and this is true for each of those lines. So this is so the lambda is not intertwined with the power counting. So the only constraint on lambda is that it needs to make this loop finite, and you have to be careful not to chop off to go into the region where you want to describe your external momenta in. So if you make it too small, you are also cutting off physics you want to describe. But beyond that, there's nothing, you don't have to be that careful about that. So I'm not an expert on that, and I don't think you have to. You make your life easier if you do, but we should be more careful there. But I don't recall that it's strictly necessary to pick this or that value. There's still some freedom in how you choose mu. Yeah, but does this require mu to be a specific value? Yeah, so again, I mean, you have been introduced to it by the person who invented it. It's been a while since I looked into that, but for the cutoff regularization, there's nothing like that. You always, regardless of what lambda you pick, these loops or their iterations are always of the same order. So you don't get a different power counting if you choose lambda to be larger or smaller, different power counting, meaning that all of a sudden these are suppressed by a certain power. This doesn't happen. Yeah. Now, so for that, you need to know that Cj is equal to some permutation operator tilde on psi I. So this is the first thing. And how do you do that? So I have my psi I, for example, expressed in the momenta, or let's do it like that. P So if a permutation operator acts on that, you get different momenta here, which then can be expressed in the momenta of a different component. And in that way, you find out that for identical particles, such an identity holds here. So you can express each of the Faddeev components, or more simply, so if you substitute those, so you make this hypothesis, you substitute this expression then in here, and you can, instead of permuting the component, you can act with the permutation operators on the T matrix, where it's more natural to interchange the particles, because what you interchange are the interacting particles, or that is, to me, very intuitive. Right, right.